Okay, so today I wanted to talk about categorification in general, I guess, and really via a specific example of a categorification of polynomials. So the hope is, because polynomials are concrete and we work with them a lot, we're very familiar with them, that it'll be nice to see an example of like categorification for this very concrete kind of object where we can really relate back to our intuition a lot. So maybe let me start by saying briefly what categorification is about. I don't even know if there's a precise way to define categorification, or if there is, I'm not enough of an expert to do so. But I think that the general vibe is probably what you would guess. You see some phenomenon in math. You think to yourself, how could I write down the definition of this thing or phenomenon or whatever in terms of category theory? How can I write down whatever it is, in this case the data of a polynomial, how can I encode that as categorical data? And then you can look at that definition, whatever you wrote down, and try to generalize all the categorical things that appear there. So for example, if you have a specific category appearing in that definition, we'll have the category of sets appearing in our categorification of polynomials. We could then generalize that and ask, okay, if we weren't dealing with the category of sets, what would the same definition look like in a different category? So that's one thing that categorification can be about. There are other things too, and it's hard for me to paint a complete picture of all the different things that categorification is. But you know it when you see it, I think, is the best thing I can say. So hopefully, at the end of this talk, you'll have seen it, and then you'll know it in the future. That's the plan. Okay, and at any time, my goal here is not to go and prove a bunch of deep theorems or anything crazy. I just really want to lay out all these ideas about this specific story with categorifying polynomials. So I'm going to try to make all the details really clear. We'll gloss over a couple things, but hopefully those things will also be clear, like how they could be filled in. So if at any point things are confusing or need more explanation or anything, feel free to interrupt me or put something in chat or anything like that. Okay. All right, so let's get into it. So we're going to try to categorify polynomials. And the general thing we're going to do is we're going to take the data of a polynomial, we're going to encode that as some kind of diagram in the category of sets, and then we're going to wonder what properties do these diagrams have, what would they look like in other categories, and questions like that. So first I should tell you what kinds of polynomials I actually care about. Yeah, we could have polynomials with coefficients in different rings or all sorts of stuff like that, and we're going to care about a very specific kind of polynomial. Namely, we're going to care about polynomials with coefficients in the natural numbers in finitely many variables. So things like the polynomial 1 is a perfectly good polynomial for us, or also like x plus y, or stuff like x squared y plus y squared x plus z plus 2 or something. Something that would not be allowed for us would be like x minus y. That's no good. We need our coefficients to be in the naturals. And that's not the naturals. Okay. Or to be precise, there's a minus 1 there that we need to avoid. Okay, so these are the kinds of polynomials.
So 0 is a natural, just making sure.
Yes, 0 is a natural number for us, as it should be. All right. So, yeah, those are the kinds of polynomials we care about. All right, and so how are we going to encode the data of a polynomial? Here's an example polynomial that I wrote down, and what we're going to do is break up this polynomial into all the different monomials that appear in, if that makes, I don't even know if monomial is the right word. Whatever I'm thinking of, like the single variables. So we have like a term with 1 in it, and that's kind of, that doesn't have any of these variables in it, so I'll just kind of leave that by itself. This x squared y term has an x and a y. There's like 3 instances of the variables that appeared there. And this term had a single copy of z. So this is what we're going to do to a polynomial. We're going to break it down in each summand. We're going to think about all the different instances of each variable that appeared and how they got multiplied together. Well, what happened was they got multiplied together. So each a polynomial consists of a bunch of terms that are added together, and each of these terms consists of just a bunch of variables that got multiplied together. And there's only finitely many variables in total. Okay, so that's the general plan. And how can we encode this as something in sets. The idea is we're going to encode the fact that we have 4 total variables appearing, this like x, x, y, and z. So I'll have those sitting around. And then I'll also want to encode how these get grouped together. So I'll want to encode that the 2 x's and the y's get grouped together into one group, and that the z is all by itself. And also I want to encode that there's another group that's kind of has nothing in there. That's this one. So these are like our 3 terms, or the 3 summands in this polynomial, and we're just identifying what are all the variables that appeared in each one. And we can encode this as a function. So let me show that on the next slide, I think. Yes. Okay. So this is a diagram of, it's just showing 3 functions of finite sets. The dots are just like each vertical collection of dots is a finite set. In this case, we have one set with elements x, y, z, one set with 4 unnamed elements, one set with 3 unnamed elements, and then one set with 1 unnamed element. Okay. And these arrows are describing functions between them. What we're saying here is I have 3 different variables that appear in this polynomial. We had the x squared y, we had the z, so in total there's variables x, y, and z. But there were 2 copies of the x that appeared. We had an x squared times the y. So to indicate that, I have this set with 4 elements here. Those 4 elements are representing all the different instances of the variables that actually appeared in the polynomial. There were 4 of those. And then for each of those instances, we need to tell ourselves which variable did it correspond to. So we had 2 copies of x, and we had 1 copy of y, and we had 1 copy of z. Okay. And then we need to tell ourselves how did those instances of the variables get grouped up. We had an x squared times a y, so we take our 2 x's and our y, and we group them together into one term here. And then we had our z, that stays by itself over here. All right, and then there was also one term that had nothing in it. So that's one of these 3 objects in this 3-element set that has nothing mapping to it, indicating it's a summand in our polynomial that has no variables appearing in it. It's going to be the empty product, so it's giving us a 1. And then finally, this last map to a single point is encoding the idea that we're taking these 3 terms that we produced and adding them together. So they're all getting added together into one kind of output term. Okay. So hopefully that's making sense. And I want to generalize our idea of polynomials very slightly by allowing ourselves to have multiple outputs in our polynomial functions. So by that I mean, well, imagine I drew this exact diagram that we had here, but instead of, hold on, my eraser isn't working for some reason, which is confounding, but okay. All right, so imagine we had a different diagram, x, y, z, same kind of setup. So I'm just copying down the exact same thing, but now I'm going to have 2 dots in this last set, 2 elements in that final set, and I'll group them together, let's say, like this. I'll have this be the function. What this would be encoding is that at the end, instead of adding all 3 of these summands together, I'm going to add the bottom 2 together, and I'm going to keep the top one by itself, and I'll have 2 different outputs. In other words, you can think of this as like a pair of polynomial functions. So one of them would just be 1. We had just an empty product being the only term in that output. And then the other output here is coming from the sum of these 2 terms. That was an x squared y plus a z. So just like kind of only partially doing the addition part. Okay, and so those are kind of the 3 steps that you need to do if you want to encode the data of some kind of polynomial function or collection of polynomials in finitely many variables. You start with all your variables, you split them up into a whole bunch of instances of each variable, you group those instances together to be multiplied together, and then you take each of those terms and you group them up to add them together. All right, so that's the vague idea. What will we do for coefficients? Great question. So we want natural number coefficients. Those are the only coefficients we're going to deal with. So stuff like 2 times x squared y, we would implement as just x squared y plus x squared y. So we'd make 2 copies of that x squared y thing. I've thought a little bit about like what would you do if you wanted to encode polynomials with like real number coefficients or something like that. And I'll mention the only thought I had on the next slide, but it seems hard to do. The natural number case is much easier, at least. But hopefully that makes sense. We could make an x squared y term and an x squared y term, and then add them together in this step here. And that would essentially give us a 2x squared y. We're not going to distinguish between 2x squared y and x squared y plus x squared y. Those are going to mean the same thing for us.
All right. Just making sure. So this encoding isn't unique, is it?
It's not unique in the sense that I could change the sets in the middle up to bijections. Like I could relabel what these elements are called, which is really why I've left them unlabeled. Their names don't matter, or what things were in there don't matter.
Okay, so but I guess what I mean is like right. So if you had like 2xy, so then essentially oh, I see. Okay. So if you had 2xy, you would basically have like, I guess, 2 of these. I guess. Sorry. Okay.
Yeah, 2 of these xy things, and like
right.
You're right that each if we choose specific sets inside for these intermediate sets here, if we choose specific things, then like we will be able to distinguish the 2 different xy's we had. So in truth, we don't really want to think about this as really a sequence of 3 functions. We want to think about it as like an equivalence class of sequences of 3 functions where we can replace the middle sets up to bijection, up to like commuting bijections. I'll make that precise in a sec. But it's roughly unique. This like picture that I drew fully encodes the data of the polynomial, and you can only encode the same polynomial via like obvious kind of permutations of this picture. Okay. So this is generally the plan we have for encoding polynomials. The data of our polynomial, or our like collection of polynomials, or whatever we're thinking about it as, consists of this set of inputs. In our case, we had the set consisting of x, y, and z. We have a set of outputs. We could have 1 output if we want to just add everything together at the end, or we could have 100 outputs if we don't want to add everything together at the end. As a side note, you can have let me back up 1 slide. We could have an output which has nothing mapping to it, and that output would be 0 because it's the empty sum. Okay. So this is generally how we are going to encode our polynomials, and as I just mentioned, it's really kind of up to isomorphism. So if I had 2 different representations of the same polynomial, what that would mean is I'd have like some sequences of maps like this. In order for these to represent the same polynomial, what's going to happen is there's going to be an isomorphism here and an isomorphism here, such that this diagram commutes. That's what it'll mean for the 2 sequences of 3 maps to represent the same polynomial. And so secretly for the rest of the talk, I'll be talking about equivalence classes of these diagrams, but I don't know. I won't say anything about the equivalence classes from now on. These polynomials really are equivalence classes, but it's not so big a deal. Yeah, most of the time we're going to be thinking about their semantics in terms of the actual polynomials they represent. Okay. So, good question. Is the collection of polynomials supposed to be ordered? Yes, it is supposed to be ordered. So notably, I'm not allowing myself to isomorph O to O prime to get the same polynomial. The O is really fixed. So we're able, if O has elements 1, 2, and 3, then there's an output 1, and there's an output 2, and there's an output 3, and those labels really matter. Yeah, so the inputs are labeled, the outputs are labeled, but the stuff in the middle, we don't really care what those sets are called. Or, yeah, hopefully that makes sense. Okay. So the observation that we should make is that polynomials can be composed. And if you're a category theorist, That's very exciting. So we know how to compose polynomials. That's a skill we all have. Even these collections of polynomials, so if I had a polynomial with a few inputs and a few outputs, let me say something like xy maps to x comma y comma x plus y or something. That's one of these kinds of polynomial maps we can think about. And then maybe I would want to compose that. I would follow this by a, b, c maps to a squared comma b squared or something. We know exactly how to do this composition. We can do it in our heads. The composition takes x comma y to x squared comma y squared. That was a really simple example, but like my claim is that we all know how to do this. Actually writing down what the composition of two polynomials is in terms of these diagrams is much more complicated. So I'll show that picture. I'll give the definition of like what happens when we compose two of these diagrams. You know, you take the two diagrams, you interpret them as polynomials, you figure out what diagram you end up with, and then you write down those functions. So here's that. Okay, it's kind of a mess, but it is a complete definition. It does work. This is how polynomials compose when we encode them as these pictures, these sequences of three maps between finite sets. So, yeah, there will be no need to memorize these equations. I just wanted to put that up there real quick to give an idea of what that, I don't know, at least to convince you that it is possible. But I should note, these composition rules, I don't know, but defining this like set A and the set B and the P and Q and all that stuff, this required a lot of the machinery of the category of sets to write down these formulas. Like we needed to use set builder notation, which is not a thing that always makes sense in any random category. So it'd be cool if we could come up with some description of how these polynomials compose, how these diagrams of finite sets compose, that's entirely written in the language of category theory instead of in the language of sets. And then we could ask ourselves, okay, what if we formed these kinds of polynomial diagrams in other categories and then use the same composition law? So I'll give an example of how that should work in a very special case, because doing the full picture is really messy. But I'll say words about that in a sec. So let's imagine I have two very simple kinds of polynomials that I'm trying to compose. Namely, one kind of polynomial where the only interesting thing that's happening is this first map from inputs to what I was calling monomials, or like the instances of the variables. This is the only non-trivial map. So we're taking a bunch of inputs, we're splitting them up into a bunch of instances, and then we're just passing those as outputs. Okay, that's the second thing we're doing. It's written on the left, so it's the thing after the thing on the right. The polynomial on the right, the only thing that's happening is we have a bunch of inputs, we do nothing to them, we don't multiply any of them together, but then we add some of them together. So here was our terms, or summands, and here's our outputs. So all we have is just a bunch of inputs. Some of them are being added to give outputs. Some of the outputs could also be 0 if they had nothing coming into them. So these are two polynomials we could write down, and I drew the functions, I drew some example functions for the non-trivial parts of those polynomials. Okay, so if we had this example with the ABC maps to A, B, B, C, following x, y, z maps to x plus y, comma 0, comma z, what would that composition look like? We can do it in our heads. We get x, y, z maps to, okay, the x plus y goes here, and then that x plus y turns into the a, and that a gets duplicated. So we get an x plus y, comma x plus y. And then our output 0 gets sent to b, which goes here. That's a 0. And then finally our output z gets sent to c, which goes here. So that would be the composition here. Hopefully that makes sense. And we can start to think to ourselves, how would I, in this very simple case, how would I construct the polynomial, or the diagram that represents the composition polynomial, just from these diagrams in kind of a category theoretic way? Okay, so the observation is that every time, the place where these functions are kind of matching up is at this set with 3 elements. The outputs to this polynomial are being the inputs to this polynomial. That's how we compose. And every time I have a term here mapping to something here, which then has an instance over here, I'm going to need an instance in my composition. Let me actually start by just writing down the diagram for this thing, if that didn't make any sense. So we would need 3 inputs, and the x term is going to have to get split into 2. We need 2 copies of x, we need 2 copies of y, and we need 1 copy of z. Like that. And then those things don't get multiplied at all, but they do get added. The x and the y get added together, and the x and the y get added together. Or wait, sorry, I did those wrong. Whoops. These have to kind of cross each other. The x and the y get added together. The x and the y get added together. The z stays by itself. Okay, and that's how that should work. And so now let me try to say the same thing again. For each of these 3 outputs of the first polynomial, inputs of the second polynomial, we need to look at all the terms that fed, we need to look at all the pairs of terms that fed into this element, paired with instances of that coming out. So like in this, the stuff I just highlighted there is we had this input like a here, which included in itself, or a came from x plus y. So there's a copy of x and a copy of y that should be inside a. And then also a needs to get duplicated twice. So we need to have a total of 4 copies of x and y. We need 2 x's and 2 y's. We need 2 x's because x is going to pair with each of these 2 terms. And we need 2 y's because y is also going to pair with each of those 2 terms. So let me try to write that down categorically. So, whoops. Okay. So the composition rules that we wanted, let me redraw that picture. We had 4 terms here. And we had 3 terms here. Okay. So now in our final thing, we're going to have 3 inputs. And let's call this, I think I called these sets something on the previous slide. We had x, y, z. I didn't really use those, but we'll do that. This will be the set x. This will be the set y. This will be the set z. And so what I want in my resulting polynomial is for each element of y, I want a thing here in my monomial term. I want an element of this set for every pair x comma z where the little x and the little z live over the same element of y. So if you're well versed in category theory, you know exactly what I'm talking about. The thing we're going to have is the pullback. So I'll describe that in a little more detail. Okay, but this is going to be the picture of the composition. So let me explain, first of all, for people who haven't seen this that often, what is this pullback, x crossover y with z? This is the set of pairs x comma z, where, let me call this function f and this function g, where f of x equals g of z. So they're the elements in x paired with the pairs of elements of x with elements in z, such that those 2 elements lived over the same thing in y. So we had an input from our first polynomial paired with an output in the second polynomial where they should interact, because the input went to this output y, and then that output y got split into some instance in z. Okay, so these are exactly the pairs of things that we have to care about, and with a little thinking, I think you can convince yourself that we need exactly this many monomials in exactly this many variable instances in our composition polynomial. this map, or sorry, this set x cross y, x cross over y with z, comes equipped with maps to x and maps to z, and those are these things here. This is the projection onto the first factor, this is the projection onto the second factor, this is going to be the identity map. And the notion of pullback is like exactly the thing we needed here. Every input gets split up into a bunch of copies, one for each of these pairs, which is exactly what we need. Hopefully that makes sense. Yeah. I think if you've seen pullbacks before, this should make a lot of sense. And if you haven't, it might still be a little spooky. But the important thing is that this construction of a pullback is not just something we can do in sets. I gave a set theoretic formula for it. But there's an instance or a notion of this in really many different kinds of categories. Any given category may or may not have pullbacks in the same way that any given category may or may not have products or coproducts. But many categories do have pullbacks, and we can form them without, we can form them by universal property, or they're described by a universal property instead of by this set theoretic construction. In the special case of the category of sets does have pullbacks in this categorical sense, and those categorical pullbacks are precisely these sets that I wrote down, these like pairs x comma z. So the category of sets has these things in particular, so we can write down the polynomial composition rule for this really specific kind of composition of two very nice polynomials, just by forming one pullback is the way we would write down that composition rule. Okay, so that seems like maybe we haven't even gotten very close to solving the problem, because we were supposed to compose arbitrary polynomials together, and the formula looked really messy. So we did handle the case where only two of the maps were not identities, and they were the two on the very outside. So that's one special case. But it turns out the nice thing here is that every polynomial can be written as a composition. So yeah, let me say it this way. If I have a polynomial like this with maps f, g, h, we can write this polynomial is equal to the composition of doing like first we do the f bit, and then we do the g bit, and then we do the h bit. In other words, first we take our variables and then we split them up into instances. Then we take those instances and we multiply them together, and then finally we take those terms and we add them together. And so to write that down diagrammatically, this would be like identity, identity, h. I'm writing the polynomial in shorthand as a triple like this, and then like this, and then like this. Okay, so this should be true for our polynomials. First we do the f part, then we do the g part, then we do the h part. We're breaking down any polynomial as a composition of three of these polynomials of very simple type that just do splitting, or just do multiplying, or just do adding. Okay, and then you can think about how do these kinds of things compose with each other. So this kind of thing in the literature is called T, and these are n's, and these are r's, and you can think about the commutation relations between your t's and your n's and your r's. And you can show what we did here, for example, is we took, we started with this one, sorry, was a t, and then this one was an r. So we did r compose t, and then we ended up writing this as t compose r in the other direction. So this did an r and then a t. Okay, so hopefully it makes sense that by just considering these special kinds of polynomials, we could figure out how all polynomials compose, and this was one example of how these special kinds of polynomials compose. We just had to have pullbacks. So these kinds of diagrams won't always have a nice way to compose in any category. We will need our category to have pullbacks in order to be able to define this nice composition rule. And in fact, we need a little bit more than pullbacks. We need exponential diagrams in general to complete this whole thing. So I don't know, that story's a little complicated. I don't want to dive too much into the weeds, but I'll just say in many categories it is possible to write down all the composition laws in a completely categorical way, so that we can interpret the composition of polynomials even when we don't have our like set theoretic polynomial semantics to rely on. Okay, so let me know if there's any questions about that. All right, and so with that out of the way, at least in the category of sets, these polynomials or these polynomial diagrams correspond exactly to polynomials. Like we've just encoded the data in a different way. So we can really form a category here. There is an identity polynomial for each, or how should I say this? What we're going to look at here, this is going to be the category of finite sets. And we're going to look at diagrams of the form like this. These are going to be the morphisms in our category. So these are morphisms from x to y in this category P are going to be these equivalence classes of polynomial diagrams. So in our category of finite sets, there will be a morphism from the set containing one element to the set containing two elements, which represents the polynomial like x maps to 1 comma 1 plus x squared or something. That would be a morphism from 1 to 2, which is precisely an equivalence class of one of these sequences of three morphisms in finite sets. Okay. And there are identity morphisms. So if I had a set with n elements and I want to have the identity morphism to the same set with n elements, this is supposed to be a collection of n polynomials, n different outputs with n different inputs. So all I do is I take my inputs and I send them straight to my outputs. So like so, that would be for n equals 3, but you can imagine any n. Okay, so we have identity morphisms. We know how these things compose, and you can check that the identity morphisms compose in the correct way. That should make sense. This is just how polynomials work. If I have a polynomial with some inputs and some outputs, and then I follow it by this like collection of polynomials that does nothing, that worked. That acted like the identity. And the same thing on the other side. So this really does form a category. The objects are exactly the same as the finite sets, but the morphisms are different. The morphisms are representing these polynomials. So that's what's going on. All right, and I put a little p subscript set here to indicate that we could replace the category of sets with any other category as long as it had enough tools to let us do these composition laws. So for example, we needed to have pullbacks in order to do the composition law of this like t with this r. And as I mentioned, we did a little bit more than that. So many categories will work, but not all of them. And the category of finite sets definitely does work. We have all our constructions there. So in the category of finite sets, we produce this category P, with P being for polynomial. The objects are finite sets. The morphisms are collections of polynomials with whatever number of inputs, with whatever number of outputs. Okay. Hopefully that's making sense. So now that we've done this, I mean, we've kind of successfully categorified polynomials. We have this like categorical encoding of the notion of a polynomial, at least with coefficients in n. And we should ask ourselves, like, what's the point? What we've really done here is kind of encoded the syntax of polynomials, or like the combinatorial structure of polynomials. We can, in this category P, we can represent collections of polynomials with coefficients in n, but the point of polynomials is not just that they have this combinatorial description, it's also that they represent functions. So what we should be looking for is some way to take all these polynomials and interpret them as functions in some context. That's what functors do. So to say that in words, what we want is to think about functors from P. In this case, I'm going to think about functors from P to the category of sets, but you could think about other things too, and we'll mention that in a little bit. But functors from P to the category of sets, what would this mean? It would mean that for every n, this n is representing like a finite set with n elements. Yeah, there are different finite sets with n elements, of course, but they're all kind of the same of isomorphism. So I'm going to imagine taking a finite set with n elements. That'll have to go to some set. So that'll map to some set. And then the set with m elements will have to map to some set. That's what a functor will do. And between these, there'll have to be an actual function. A morphism in the category of sets. And I guess I've been a little confusing because on the previous slide, I said P subset, where I meant here the category of finite sets, and here I want to use all sets, so maybe to fix that for myself right now, save us the pain of bad notation, I'll use all uppercase letters when we're doing all sets. Okay. So that's what a functor should do. It should take each of these objects in our category P, which are just the finite sets. So those are basically specified by a natural number. It should produce some set from each of those with some function between them. All right, and this will be a way to kind of interpret the syntax of polynomials in some way, to have some semantics for polynomials. Okay, one kind of functor we can always make is like a constant functor. We could send all the objects of P to a single set and all the morphisms to the identity map. And that's always a functor, like no matter what categories you started with. It's kind of boring for us because it doesn't give us any interesting semantics for our polynomials. Instead, what we should be looking for is maybe something more like the following example. Let's say we took n and produced the set z to the n, and m and produced the set z to the m, and then the function between them is literally given by the polynomial. Or like, the thing we have in our heads is the polynomial, not the diagram. So like if this polynomial map, if we were thinking about the polynomial map xy maps to x squared comma xy or something, this makes perfect sense as a function from z squared to z squared. So we can interpret our polynomials in this way, and they'll compose in the correct ways because we wrote down like literal polynomial maps. So hopefully it's clear that this would actually form a functor. We can interpret our stuff in this way. And this worked because all the elements of z can be added together, it can be multiplied. There is a thing called 0, there's a thing called 1, etc. But z is maybe even a little too strong. Like we didn't need all of the structure of z because we only have natural number coefficients. There's no need to ever have any negative numbers. So we could have also done something like this. Functions from here to here. Xy maps to x squared comma xy also makes perfect sense as a function from n squared to n squared. And they compose in the right way, etc. So these are two different functors that I've written down. There are many of these, but the interesting result that we'll be able to do today is to actually classify all the interesting ones. So again, like functors like the constant functor, uninteresting. Functors like this, that like realize polynomials as actually interesting kind of polynomially maps between these powers of these rings or semirings or whatever, those are more interesting. So what can we do to distinguish these interesting functors from the non-interesting functors? I think the observation we should make is that the set with n elements should somehow correspond to like an n-dimensional object, because we want our polynomials to turn into actual functions, and this polynomial is supposed to have n inputs and m outputs. So the domain of this corresponding function should be somehow n-dimensional, so we can take n inputs from there. And then the output should be, the codomain should be m-dimensional, so that we can have m different outputs. And if that's the case, then when I take like let's say I have a functor f from P to set. If I do f of n cross f of m, this should be like my n-dimensional object cross an m-dimensional object. This should be an n plus m dimensional object. Which in the category of finite sets, this is accomplished by disjoint union. So, what are the interesting polynomials? The polynomials are going to be interesting. I don't have too much room here. Okay, I guess I can zoom. Great. The polynomials are going to be more interesting when we have the equation or something. When I input a disjoint union of two finite sets, I should get out the product of those objects. So this is the kind of condition I want for my functor. It turns out, actually, that this disjoint union is the product in the category P. Which is kind of confusing. The disjoint union is the coproduct in the category of finite sets, but in the category P, which has the same objects but different morphisms, the coproduct is now the product, or the disjoint union is now the product. And the reason that happens is just that if I think about polynomials from x over to y1 disjoint union y2, this is polynomials with this many inputs, where I want these as outputs. But that's the same as just like first taking this many inputs and producing these outputs, and then also taking this many inputs and producing these outputs. So polynomials from polynomial diagrams with inputs x and outputs y1 disjoint union y2, those are the same as pairs of polynomial diagrams with input x and output y1, input x with output y2. That's exactly what it means for y1 disjoint union y2 to be the product of y1 and y2 in this category P. Okay, so this condition we can write as saying that F preserves products. Just a side note. But you're free to think about it as just this explicit condition. I really want it to be a little stronger. I don't want there to just exist an isomorphism. I want there to be a natural isomorphism induced by the natural maps. The x disjoint union y comes with projections down to x and down to y, and those, when we apply f, give us maps from f of x disjoint union y to f of x and to f of y, and then I can take the product of those maps, and so there's a natural function from here to here, which we want to be a natural iso. Okay, but don't worry about that too much if natural transformations are spooky. The idea is just that I want my interesting functors to preserve this property, so that it really feels like the finite sets are being sent to objects of the correct dimension. When we take their product in the category of sets, their dimension's ed. All right, so let me make a definition of a term that actually appears in the literature. Tambara functor, I should go capital T, because it is a person's name. Also called a TNR functor for the factorization reasons we talked about earlier. So this is a product-preserving functor. From our category P to the category of sets. And more generally in the literature, we allow ourselves to change this P sub category of finite sets. We allow this thing to change to be other different categories. Most importantly, G sets is the other interesting example. But this is at least a special case of the notion of Tambara functor. Okay. So that's all I wanted to do on this slide, just define what is a Tambara functor. And I want to point out also that the interesting examples of Tambara functors that we've seen so far, the only examples that we've seen so far, are of the form where we take a set with n elements, and then, let me just write it this way, we take a finite set x, and then we produce like z to the x, or n to the x, or really it could be any r to the x, where r, it needs to have a 0, because we have zeros as possible outputs of our polynomials. It needs to have a 1. It needs to have some way to add. It needs to have some way to multiply. And the composition of polynomials needs to work semantically for elements of R. So we need stuff like that multiplication distributes over addition and things like that. So what kind of structure has all those things? It's commutative semirings. Let me just define what those are. Okay, commutative semiring is a triple. So it's like this. We got plus, we got times, and it's going to be exactly like a normal ring, unital associative. The only thing is that we're not necessarily going to have additive inverses. So under addition, we should have a commutative monoid. Under multiplication, R, this should also be a commutative monoid. And then finally, distributivity. So exactly the same as a normal unital associative ring, commutative, I guess, normal commutative ring, except we don't necessarily have additive inverses. So n fits this definition, whereas it wouldn't have been a ring. And any ring does as well, so z and stuff. Okay, and the interesting fact, the reason why we haven't seen any other interesting examples of Tambara functors, other ways to like semantically interpret our polynomial syntax, those don't exist. Every Tambara functor from the category of P is one of these. It's at least naturally isomorphic to the functor that takes a finite set x to the functions from x to a particular commutative semiring. So that is the proof I will try to explain now. Okay, hopefully it's clear what we're trying to show here. Let me know if it's not. Basically, what we need to do is show that any product-preserving functor from the category P, any functor which sends disjoint unions to products, is of the form takes one of these finite sets and just gives us commutative semiring to that power. Okay, so how is that going to work? Well, if this is going to be the case, well, let's have our let's give our functor a name. Let's say A from P to set. I forgot to do capital letters. Okay, so let's say this is a 10 bar functor. That's just one of our interesting functors. If this is going to be the case, then our hope is that A of x is just r the x for some fixed r. Okay, that'll be true. And so how are we going to prove it? How can we identify what r is supposed to be? Well, r is just r to the 1. So we simply take, let's define r to be A of a singleton set. Just pick your favorite singleton set, could be like the set of the empty set or whatever, and then fix that, call that 1. And then we'll take the image of that under this functor, and we'll call that r. And now we're going to prove, at least right now, that r is just a set. It's just a set we produced by applying this functor. But we can wonder, how can we give this the structure of a commutative semiring, and then show that all the functor stuff works. So I'll mostly explain how does R become a commutative semiring? Where does the commutative semiring structure on R come from? Okay, so if I want to have a commutative semiring structure on R, what I'm supposed to do is have functions from R cross R to R, namely addition and multiplication. So how would I get addition? Well, R is A of 1, and R cross R will then be A of 1 cross A of 1. But remember that A of 1 cross A of 1 is supposed to be isomorphic to A of 1 disjoint union 1, which I'll call A of 2. Pick your favorite 2-element set. Well, I guess really my definition of 2 is it's our favorite 1-element set, disjoint union our favorite 1-element set. That's our 2. Okay, so if A of 1 disjoint union 1 is the same as A of 2, then all we need is a map from A of 2 to A of 1. And that should come from a polynomial from 2 to 1 in P. This would be a polynomial with 2 inputs and 1 output. And it's supposed to correspond to addition somehow. So this is kind of an obvious choice. We want this polynomial. All right, that's certainly a thing in our category P. So I can apply A, and I get a function from A of 2 to A of 1. And A of 1 was what we called R, and A of 2 is R cross R, by the fact that A of 2 is A of 1 disjoint union 1, and that's A of 1 cross A of 1. So we can produce this function that we're going to call plus. And it's just the thing that comes from A, comes via A from this like addition polynomial x comma y maps to x plus y. Hopefully that's making sense. I haven't yet shown that this has any of the nice properties that we need, but it's certainly a function. And of course we can do the same thing for multiplication with x comma y maps to x times y. So now we're going to have these functions from R cross R. To R, we have our plus and times, which came from our functor A applied to those particular polynomials. Excuse me. So how are we going to show that the axioms of a commutative semiring hold? Well, we need to show, for example, that R is a monoid under addition. What that means, well, one of the things that means is that the addition has to be associative. So let me write down a diagram that encodes that. You might have seen this before. Okay, so what these things are doing, I'm starting with some input a comma b comma c, and then first, if I go this way, I'm going to add the first two, a plus b comma c. That's what the plus cross ID does. Add the first two inputs, do nothing to the third. And then I can send that down to a plus b plus c. I add that stuff together. Or I can start here, and I can get, I should really write it as a plus b plus c like that. Also, sorry that's such a bright color. It shows up differently on my tablet. That looks a little painful. Okay, but so this otherwise would map to a comma b plus c, and then we can send that over to get a plus b plus c. And in order to be associative, we need that these two things are equal. In other words, we need that this diagram commutes. So that would be the axiom that we need to verify, is that this diagram commutes with these particular maps, these pluses. But these pluses came from A, and A also preserves identity morphisms. Every functor does. So I can see that this commutative square that I want is the image of a square in the category P. So in the category P, there's a square like this, where this is the polynomial x, y, z maps to x plus y comma z, maps to x plus y plus z, and this goes to x comma y plus z, and that goes to x plus y plus z. And in the category P, because these are like formal polynomials, syntactically this diagram does commute. So that one's really good. Just because we're composing like formal polynomials in the category P, and polynomial addition is associative. Like, that's built into the way we define the category P. Okay, so because this diagram commutes in the category P, we just apply the functor A, and we get the corresponding commutative diagram in the category of sets, verifying that our addition operation is actually associative on R. And you can do the exact same thing for any of the other axioms of a commutative semiring. You verify all the other properties of addition, all the other properties of multiplication this way, and the distributivity is also the same. These all follow from the fact that our maps defining the addition and multiplication, this like x comma y maps to x plus y, the x comma y maps to x times y, those have the right composition properties with each other inside the category of polynomials, because that's how our polynomial syntax works. Okay. So hopefully that makes sense. And that shows that that A of 1 is going to be a commutative semiring, this thing R. And then for any other input, if I have A of x, well, that's just A of the disjoint union over all elements of x of the singleton set of that element. And as we know, that's isomorphic, or by assumption on A. These are supposed to turn disjoint unions into products. This is the product over all x and x of that thing. And any singleton set is isomorphic to 1. So this is the product over x of just a bunch of copies of our ring R, which is what we wanted. That's R to the x. So I haven't shown that the morphisms that A produces, where like you have A, you have some morphism in P, and you apply A to that, you get some morphism in the category of sets. I haven't shown that those morphisms are precisely the things we wanted from our functor that sends a commutative semiring R to the x, or yeah, the functor that we're trying to get here, the thing that takes a finite set x to R to the x, and then takes a polynomial to like actually that polynomial on inputs and outputs in R to the x, from R to the x to R to the y or whatever. Those morphisms, we haven't checked that those actually correspond correctly, but they do. And it's basically because every polynomial can be built up via addition and multiplication. You also have to check that the 0 and 1 work, and yeah, so there's some details here that I'm omitting. Mostly because I am talking slower than I anticipated. But all this stuff can be checked, and so it is really true that every one of these interesting functors corresponds to a commutative semiring. The functors we get from the category P to the category of sets that are interesting are precisely just take a finite set and look at maps from that finite set to a fixed commutative semiring. That's like those are the only ways, those are the only semantics we have for our polynomial syntax in the category of sets. Okay, so from here, there's a few things we could do. Before I go on to this slide, actually, let me just say that. We could either generalize the category we were working in to start with. Instead of looking at those diagrams in sets, we could look at those diagrams in G sets or whatever. Alternatively, we could change the codomain of our functors. So maybe we want our temp functors, instead of going to set, which this should be capital set, instead of going to set, we could go to something else. But that won't be very interesting. It turns out, if you're familiar with this concept, and you think about this enough, the category P that we defined is precisely a Liouville theory for the theory of commutative semirings. So if you look at functors from this P into other categories, what you're going to get is just commutative semiring objects in those categories. So if you did this into abelian groups, you would get commutative semiring objects in abelian groups, and those, I guess, are actually commutative rings. Yeah, so there's you could do this in any other category, but it doesn't give us anything like super new. We just get commutative semiring objects in those other categories. And in the category of sets, the commutative semiring objects are commutative semirings. Okay, so that's not as interesting. What's more interesting is to change the category over which we began working, like the category of finite sets, where we had these like diagrams of functions between finite sets encoding the data of polynomials. What if we wrote down those same diagrams with the same composition laws in any other category, as long as we have pullbacks and exponential diagrams and such? So we can do that. And I think I'll talk about that instead of doing the slide. So for other categories, the most interesting case, I think, which is also relatively easy to get your hands on, is where we use finite G sets. So you could do this for some group G. Let's do it for a finite group, just to make things more concrete. And this category of finite G sets has all the nice constructions that we need to make things work. It has pullbacks, it has those exponential diagrams that I mentioned. All the composition laws we wanted to define for polynomials can also be defined in this category of finite G sets. So it makes perfect sense to make this category P sub G set. Yeah, this is category of finite G sets, which I should say, a G set is a set with an action of G on it. Okay. So we can do this in that case, and then the theory of Tambara functors becomes a little more interesting, because it's no longer the case that our functors from this P sub G set to the category of all sets that preserve products, those Tambara functors are no longer just given by commutative semirings, or even commutative semirings with an action of G. It turns any commutative semiring with an action of G on it will give you one of these Tambara functors, but there are others besides those. So the theory becomes interesting over this other category. And there are tons of contexts where you could do this. The thing you need is really a locally Cartesian closed category. Excuse me. So this C could be anything locally Cartesian closed. So if you're familiar with those words, that might be interesting. So in particular, finite G sets. And for finite G sets, there are really other interesting examples. And you get, you could imagine these like this collection of Tambara functors. You get all the functors that turn coproducts, that turn disjoint unions into products from P sub G set to the category of all sets. Those things are kind of like some G equivariant version of commutative semirings. You could think of them that way at least. Because in the case where G is the trivial group, you get just the category of finite sets, and then we're back to just normal commutative semirings. And so if you change G to be some other, non-trivial group, then we might have some interesting, like, weird generalization of commutative semiring in a G equivariant context. Okay, so that's one way in which this categorification story can maybe be helpful or interesting or something, is that it gives us this generalization where there's some interesting theory to be explored, whereas, originally polynomials with coefficients in n, relatively boring. So that is, I think, where I will stop. If you want to learn more about this stuff, may I recommend these sources. In particular, Strickland's paper called Tambara functors is very terse and straight to the point, but doesn't have a lot of exposition, but it is very nicely done. Like, all the stuff is correct, and it's very clean. So I'd recommend that if you just want to learn this theory and see all the details that I might have omitted in this talk. These other papers are also really interesting and have more exposition. Tambara's paper is where this stuff all came from, in some sense. Okay, so thanks for coming, and let me know if you have any questions.